The next thing we're going to do is we're going to talk about plane waves in arbitrary directions. So far we've talked a lot about plane waves that have phase dependence that looks like e to the minus j beta z, or e to the minus jkx, or e to the jky. That's fine. But plane waves can actually propagate in directions that are not along principal axes. All you need to specify a plane wave is a unit vector in the direction of propagation, all the material parameters, the amplitude and frequency of the wave, and you actually only need the amplitude of E or H because you can always find one from the other, and a polarization vector for either E or H. The reason this works is that you can specify any plane if you know the unit vector that is perpendicular to the plane and any point that the plane passes through. In fact, it doesn't even have to be a unit vector, but it's convenient if it is. Then, if you have any point R on that plane, so let me draw a plane and show you actually. Let's say this is R0, the location of a point that the plane passes through. And here is our surface normal unit vector, that's U hat. And let's say I choose some other point over here. That's R. R minus R0 is going to be like that. And then all I have to do is note that since R minus R0 is perpendicular to this unit vector, because it lies in the plane and the unit vector is perpendicular to the plane, their dot product is going to be 0. So that specifies the plane. The set of all the points R for which this equation is true tells me about this plane. And another important fact is that I can also write it as R dot U hat equals some constant value. And yes, I picked phi for a reason. Because dot products obey the distributive property. So all I'm doing here is just saying that this thing has the value of R0 dot U. So think about this in terms of a plane wave now. If I want to specify a wave with planar phase fronts, I need something in the argument of my phase exponential. Instead of e to the j beta z, I need to change that to be e to the j, something that is constant on these planes that are perpendicular to my direction of propagation. So e to the j r dot u hat, but I'm going to name it UK, and then I'm going to multiply it by my wave number also, because we also have to accumulate phase at a rate. So usually we write that not in this order. Instead, we write it as e to the j k dot r, where k here is now a wave vector, and its amplitude, its magnitude is k, the wave number, and its direction is u hat k, the unit vector along the direction of propagation. So if propagation happens to be along the z direction, then you end up with e to the minus, oh, I need a minus sign on these, e to the minus jkz. Fine. But if this propagation vector points in a different, more complicated direction, it could involve all of the different components. And then it often ends up being e to the minus j k sub x x, that's the x component of the k vector, plus k sub y y, that's the y component of the k vector, plus k sub z z, that's the z component of the k vector. And all of these things can be found using sines and cosines of the various angles that you can use to specify u sub k. Let's do an example about this. It's really nice because this dot product formulation lets you specify plane waves in whatever direction you want. So let's specify a plane wave in whatever direction we want. I'm going to choose a unit vector. And it is not allowed to be along any of the primary axes. So I'm going to say u sub k is equal to x hat plus y hat plus z hat, and then I need to make it a unit vector, so I'm going to divide by √3. Now, I've got a frequency is 300 megahertz. The electric field amplitude is E naught, and the wave is propagating in air, so that's epsilon naught and mu naught. No material parameters really to worry about here. Based on the frequency and the fact of air, I know that the wavelength is the speed of light divided by the frequency, which is 1 meter. And I know that the intrinsic impedance is the square root of mu naught over epsilon naught, which is 377 ohms. And then last, I'm going to say that the electric field is linearly polarized and perpendicular to Z. All right, how do I work that out? Well, since the electric field has to be linearly polarized and perpendicular to Z, I'm going to say that the electric field polarization vector, I'm going to give it a UE hat, is just going to be Z cross the propagation vector, and then I'm going to divide it by the magnitude of that so it stays a unit vector. Now when I'm working out this cross product, I like to use the determinant method. So I do x hat, y hat, z hat, and then I do the next vector is 0, 0, 1, and the next vector is 1 over √3 in all the components. And what I get when I work that out is x hat times minus 1 over √3 plus y hat times, oh, and then I have to divide up here by z hat cross UK magnitude, almost forgot. Y hat times 1 over √3, no z component, as you can see, So I have to do that and then divide by its magnitude, which is root 2 over root 3. So what I get is minus x hat over root 2 plus y hat over root 2 as my electric field polarization vector. Putting all of that stuff together now, I have that the electric field for this plane wave is E naught times minus x hat over root 2 plus y hat over root 2 times e to the minus j k x over root 3 plus y over root 3 plus z over root 3. And we should remember here that k, the wave number, is 2 pi over lambda. And since lambda is 1 meter, that k is actually just 2 pi. That's my electric field here. If I want to know the magnetic field, I can say, well, the magnitude of the magnetic field is E naught over eta, and we know eta is 377, so we can put that in there. And the vector direction of the magnetic field is E cross H is in the propagation direction, so H cross propagation direction should be in the E direction. So actually it is a Z-directed magnetic field because we already did that math problem before. And then it's got all the same phase dependence as previously, e to the minus j 2 pi over root 3 x plus y plus z. I factored out the root 3 so it would take less space to write. That's all. So there's an example about plane waves in arbitrary directions. Your activity is about finding the total power radiated by the sun and the electric and magnetic field intensities on the Earth's on the Earth's surface and the power density of solar radiation on the surface of Mars. That's a fun one. So enjoy that. Remember to post your responses on the discussion board.